Hello and welcome back to the Deep Learning course. This week, we'll discuss regularization methods that allow us to restrict the capacity of our networks in order to generalize better to unseen data. Regularization is a crucial part of deep learning and also one of the components that you can play with in practice in order to actually get better performance. So it's important to understand this in detail. In this first video, we'll get started by providing some motivation for why regularization is particularly important in the context of deep learning. Let's dive right in. Motivation for regularization in deep learning. To motivate regularization, let's have a look at typical learning curves for the training set loss and for the validation set loss. So training set loss, typically if your optimization works well, goes down very quickly towards close to zero. Validation loss, on the other hand, doesn't always go to zero. Instead, typically at some point, maybe roughly here, you reach a minimum and then you don't get much better, or actually, as in this case here, you get ever so slightly worse over time. And the goal of regularization is to achieve the best validation loss we can obtain, so the best generalization that we can obtain. Let's have a look at the bias and variance trade-off of deep neural networks. So in a standard machine learning class, you would have seen a standard decomposition of the bias and variance of the generalization error, in this case here for mean squared error, as follows. So the expected loss is the bias squared plus a variance plus some noise term. And deep neural networks, they have very low bias and they have high variance. The noise term, well, that's the noise of the data. We can't actually do anything about that, but we can change bias and variance. And deep neural networks, now, well, they have a very low bias. In fact, they can represent any function. In fact, they can even perfectly fit random noise. So if you make them large enough, in the limit, actually the bias will go towards zero because it can really fit any function, any Boolean function, according to the universal function representation theorem. And on the other hand, however, they have high variance. So what that means, as a refresher, if you change the training data a little bit, then the function that the neural network fits may actually change a lot. And that makes them relatively brittle, and that's why this variance goes into this expected loss term here. Now, the goal of regularization is to introduce some bias in order to substantially reduce the variance to make them less brittle, and therefore then lead to a lower generalization loss. Now, one very simple method of achieving that is to stop training when the error on the validation set has reached its minimum. So in this cartoon figure here, we have the minimum of the validation error at this point, and so we would early stop at that point. This then often actually trains only for a few epochs, and if you actually combine this with initializing with relatively small weights, then that also relates to a preference for small weights, as we will see in later videos. This is a very simple and popular heuristic. The only thing is you need a validation set in order to perpetually observe the validation error. All right, this already brings us to the end of this short video. And as always, I'd like to leave you with some questions. I encourage you to pause the video and think about them before moving on. And I'll see you in the next video. Thank you.